Hello everyone, welcome to our project presentation, VaultShare, an end-to-end encrypted file sharing platform built on a zero-knowledge architecture. The main idea behind it is very simple. Most cloud storage platforms today require users to trust the provider with their files and encryption keys. With VaultShare, we wanted to build a platform where the server itself is mathematically incapable of reading user data. Today's services like Google Drive, Dropbox, and OneDrive are extremely convenient, but they all share the same security issue. The provider can technically access uploaded files because either the files are stored and encrypted or the provider controls the encryption keys. This creates several major risks. First, confidentiality risks. Sensitive documents such as medical records, contracts, or financial files could be exposed through breaches or insider access. Second, metadata leakage. Even if the file content is encrypted, file names and file types can still reveal important information. Third, centralized key custody. If encryption keys are stored on servers, compromises all users. And finally, cross-device access usually sacrifices privacy by syncing keys through the cloud. So the question we asked was, build a cloud storage platform that remains convenient while eliminating server trust completely? VaultShare is the solution. It is a privacy-first file sharing platform based on zero-knowledge principles. The core idea is, all encryption and decryption happen exclusively inside the user's browser. The server only stores encrypted data that it cannot decrypt. We also added secure public link sharing, cross-device recovery, multilingual support, and responsive modern interface. Now, let's briefly look at the architecture of the system. VaultShare uses a modern, full-stack architecture. On the front end, we used React 19 with TypeScript and Vite. For styling and animation, we use Tailwind, CSS, and FrameMotion. The backend infrastructure is powered by Supabase, which provides authentication, PostgreSQL database services, and encrypted file storage. For serverless operations, we use Versal Edge functions. All cryptographic operations rely entirely on the browser-native Web Crypto API. This means we do not depend on third-party cryptographic libraries. One important architectural principle is that encryption occurs before upload. At no point does unencrypted data leave the browser. Let's now explain the encryption pipeline. When the user uploads a file, 5 major steps occur. First, the browser generates a random 256-bit AES key. Second, the file itself is encrypted using AES 256 GSM with a random initialization vector. Third, metadata such as the file name and MIME type are also encrypted to prevent metadata leakage. Fourth, the AES key is wrapped using the user's RSA 496 public key. And finally, only ciphertext is uploaded to the cloud. The encrypted file goes to Supabase storage, while encrypted metadata and wrapped keys are stored in PostgreSQL. This architecture ensures the server never receives plain text files or raw encryption keys. We also implemented secure cross-device recovery. Users can export an encrypted backup for their RSA private key. This backup is protected using a separate password and stored locally by the user. When moving to a new device, the user imports the encrypted backup file, enters the backup password, and the private key is restored locally in the browser. Again, the server never stores or accesses private keys. Let's now demonstrate. Here we can see the landing page of VaultShare. The platform supports both light mode and dark mode. We also implemented multilingual support with English, French, Arabic, including full right-to-left layout support for Arabic. Now I will create an account and log in. After authentication, the user reaches the dashboard where uploaded encrypted files are managed. Now, I will upload a file. Once the file is selected, encryption begins locally in the browser. At this stage, the AES file key is generated, the file is encrypted, metadata is encrypted, and the AES key is wrapped using RSA. Only after encryption finishes, the upload starts. Now, the encrypted file appears in the dashboard. Next, I will generate a secure public sharing link. Here we can access the generated link. Notice that the decryption key included in the URL fragment after the hashtag symbol. This means the server never sees the key. I will open the shared file. The browser extracts the decryption key locally, retrieves the encrypted file, and decrypts it directly inside the browser. The server only serves ciphertext throughout the entire process. Finally, here is the secure backup and recovery feature. The user can export an encrypted private key backup file and later restore it on another device. This enables cross-device access without compromising the zero-knowledge architecture. During testing, we verified several important security properties. First, no key material is transmitted to the server. Second, metadata remains encrypted in the database. Third, public sharing links never expose decryption keys to the backend. Third, public sharing links never expose decryption keys to the backend. We also implemented row-level security policies directly at the PostgreSQL engine level. From a performance perspective, the platform remains responsive even during large uploads because cryptographic operations run inside web workers. We achieved smooth UI responsiveness and efficient encryption performance with files up to several gigabytes. To conclude, VaultShare demonstrates that it is possible to build a production-ready cloud storage platform with mathematically provable privacy. By moving all cryptographic operations entirely to the client side, we eliminate the need to trust the server with sensitive data. VaultShare combines security, usability, and accessibility into a single modern platform. Thank you for watching.